We use an apparatus that allows a copper plate to swing back and forth through a magnetic field like a pendulum. The plane in which the copper plate swings is parallel to the plane of the plate and normal to the direction of the magnetic field. As the copper plate enters the field, the changing magnetic flux induces an EMF in the plate, which in turn causes the free electrons in the plate to move, producing circulating eddy currents. Note that the magnetic field is directed from the north pole to the south pole of the magnet that provides the field. When viewed from the north pole side of the magnet, the induced eddy current is counterclockwise as the plate enters the field. As the plate enters the magnetic field, the external magnetic flux through the plate increases. Hence, by Lenz's law, the induced current must provide effective magnetic poles on the plate that are repelled by the poles of the magnet. Thus, here a north pole is induced over the surface of the plate facing the north pole of the magnet. As the plate leaves the magnetic field, the external magnetic flux through the plate decreases. Hence, again as per Lenz's law, the induced current must provide a magnetic south pole on the surface of the plate facing the north pole of the magnet. This is quite opposite to the case when the plate enters the magnetic field. The induced eddy current always produces a retarding force Fb when the plate enters or leaves the field. This retarding force slows down the swinging of the plate and eventually brings it to rest. Thus, the oscillations of the plate are damped. When rectangular slots are cut in the plate, eddy currents and the corresponding retarding force are greatly reduced. This reduction in the retarding force is because the rectangular cuts in the plate prevent the formation of large current loops. Hence, the pendulum plate with holes or slots reduces electromagnetic damping and the plate swings more freely. Let us now explore the uses of eddy currents. Eddy currents are produced when a metal plate is subjected to a changing magnetic field, heats it. Hence, these currents are unwanted in certain situations. Reduction in the surface area of the plate helps in reducing eddy currents in the metallic cores of transformers, electric motors, and other such devices, in which a coil is wound over a metallic core. Eddy currents are minimized by using laminations of metal to make a metal core instead of using a single metal piece. The laminations are separated by an insulating material like lacquer. The plane of the laminations is arranged parallel to the magnetic field such that it cuts across the eddy current paths. This arrangement reduces the strength of the eddy currents. Since the dissipation of electric energy into heat depends on the square of the strength of the electric current, heat loss is substantially reduced. Let us now study the applications of eddy currents. Strong electromagnets are situated above the rails in some electrically powered trains. When the electromagnets are activated, the eddy currents induced in the rails oppose the motion of the train. As there are no mechanical linkages, the braking effect of the train is smooth.
like to do another demonstration of eddy currents and the resulting magnetic braking that will occur on a pendulum. So what I have here are two magnets. Okay, so this is like the north pole here of this magnet and the south pole here of this magnet. So there's a fairly uniform field in between here, and these are actually fairly strong magnets. So if I actually put a piece of steel in here, if this were a piece of steel, it would stick and I probably wouldn't be strong enough to pull it apart. But what I have here is a piece of aluminum. Okay, so aluminum is paramagnetic, so it is only weakly magnetized, so it's not really attracted to the magnets. Okay, so I also have two other pendulums. Okay, this one has slots in it, and this one, the slots go all the way to the bottom, so there's no connection along the bottom. Any of these I put in here will freely swing. Okay, so now let's see what happens when I try to swing this one through the magnetic field. Okay, notice how it breaks and stops. Now if I did the one with the slots, we see it also breaks and stops, not quite as quickly. And finally, the ones with the grooves, so that there's no connection on the bottom, swings freely. Okay, what is happening is that as this one is swinging into the field, you have a changing magnetic field in this region. So that sets up a resulting current such that the magnetic field generated by the current opposes the increase in magnetic field. So that will be a field in the opposite direction, and that is what's causing the braking. Whereas in this one, where we have these grooves, you can't get the circulating eddy currents because of the disconnection between these regions of the metal, and that's why you don't set up those strong induced magnetic field currents and resulting magnetic fields.
Here is how it applies to the walk-through metal detector. The walk-through metal detector has coils of wire embedded in the sides that create a magnetic field. This is referred to as pulse induction technology. A short burst of current passes through the coil. Each pulse generates a short magnetic field. When a person walks through the metal detector, the magnetic pulse is sent into the opening. If the person is carrying a metal object, there will be a return magnetic field that will be detected by the electronics. The latest walk-through detectors have multiple coils. Each of the coils creates a separate magnetic field that defines the location of the object.